In this section, we will investigate internal model control. This is a model-based control strategy that we have implemented during the control lab associated to the course Fundamentals of Control Theory. So let's first have a look at what we mean by model-based control, and for that we go back to the structure of a controller, and we remember that we have first input processing, so processing of the input information, for instance filtering, normalization and so on. Then you have the control processing, the control algorithm, and then finally output processing, so the processing of MV, so for instance or saturation of MV, denormalization, interlocks and so on. It is the control algorithm that determines the name of the controller. So if the algorithm is a PID type algorithm, you have a PID controller. If it is containing fuzzy logic, it's a fuzzy controller, and if it is containing a model to construct MV, then it's a model-based controller. So for instance, a Smith predictor is a hybrid type controller because the control algorithm is PID and the model is used in the input processing to construct the predicted PV. When should model-based control be used? Well, of course, when the PID controller has limitations, and we have seen previously that when the dead time is large with respect to the main time constant, when the controllability ratio is high, well, then the PID controller has problems. And in the case of complex dynamics, so for instance, well, high order lag systems, systems with oscillatory modes, and systems with inverse responses, right? So we see here that the internal model controller, or in general a model-based controller, is also an alternative of the Smith predictor for systems with a high dead time with respect to the main time constant, or predictive PID controllers for processes with an inverse response. Well, model-based control has also advantages in the case of the multivariable situation, and when we have coupling, in the presence of constraints. We have seen in the simulations for override control that we had to violate the limitation, the constraint, slightly with this solution, and it also offers the possibility to do optimization. Right, this will not be explored in this course because we are going to stick to IMC, internal model control, without constraints and in the single input single output case. But students in control engineering have explored the other way, which is to use model predictive control. If we now compare internal model control and PID control, we will see that, well, the internal model controller is a proactive controller since it is using a model, so a relation between MV and PV, whereas the PID controller is using the control error, so it is a reactive controller. The IMC controller is usually used at a supervisory level to set points for the PID controller. So it's used in a cascade and it is used as the primary or a master controller in the cascade. We are not going to explore this in this course, but you can implement an internal model controller without the need of constant sampling instance. So that's, well, the sampling instance can vary from one period to another, from one sampling instant to another. As the name suggests, internal model control uses a model, and this model can also be used for other purposes. For instance, understanding the process better, offline simulation, and of course online simulation. And if you do online simulation, compare the simulation with the actual process and show the discrepancy with the process. So a discrepancy can be a sign of a bad model, but it could be also a sign that there is something wrong on the actual system. So the model can then be used for fault detection, for instance. Well, if you have to implement this internal model controller yourself in an FP, this is going to be work intensive, and you're going to do it only if there is an economical incentive. Remember that if you implement a control algorithm yourself, you're going to have to implement all modes: manual, automatic, internal, external, interlocks, a human machine interface, and so on. Well, to be honest, this internal model controller is now becoming more and more available in a standard fashion in the control libraries of the vendors, so that you can use internal model control without all this work. Another model-based approach that goes beyond the scope of this course is model predictive control, and this is a control strategy that students in control engineering have explored with my colleague Thomas Muser. Model predictive control contains the following three ideas. Well, an explicit use of the model to predict the process along a future time horizon, right? And then the calculation of the optimal control sequence over this horizon, and a receding horizon strategy. This means that we take the first control signal of the control sequence that has been computed over here and we apply it, and at the next sampling instant we redo the optimization within a horizon that has shifted by one sampling interval. To calculate this optimal control sequence, we'll have to optimize a performance index. Without going into the details, this performance index penalizes over the time horizon the difference between the set point and PV, so the control error, but it also penalizes the control energy that is involved. So here is a representation that allows you to understand things. So here is the present, and at the present time you do the optimization. So here we have the reference trajectory, which is really the set point, and over an horizon, right, you compute the optimal control sequence to go to this set point. And using this control strategy, you can see that the predicted output will go to the reference strategy, and what is done is to apply, well, the first control in this sequence, right? And at the next sampling instant, here k+1, we'll redo the optimization exercise with a prediction horizon that has shifted by 1, and this will allow us to react to disturbances in the process. The idea is that we kind of build up the internal model from scratch so that you understand the ideas that are behind this control strategy. We assume that the process is described by a transfer function P that describes the dynamics of the system, and that we can split P into, well, a static gain and another transfer function that describes the dynamics but that has gain 1. Let us illustrate this using a Broida model. So we have the gain, time constant, and the delay. So this one over here is 1 over ts plus 1 exponential of minus theta s, right? And you can see that indeed P is this one times kp. And if we look at this process over here that describes the dynamics, we have also associated to that a static process that only describes the, well, static process, and the interpretation is that if we have a constant input and we put it at the input of the system and we wait long enough so that we look at the steady state output, well, this steady state output will be, of course, the static gain times the input by definition of the static gain. Of course, to construct our internal model controller, we are going to base our control strategy on a model of the process, and to distinguish between the model and the actual process, well, we'll call the process P and the model P hat, right? And what we have done for the process, we can do also for the model. So we can separate things so that you have the static gain KP hat and a transfer function here that only takes into account the dynamics and has gain 1. So associated to the model, you have also a static model that only takes into account the static part, so the static gain of the model. Well, let us have a look at the main idea that is behind internal model control. And well, this leads to this step 1, static optimization. So what we do is start from the static model that is given over here, right? And in steady state, what we would like is that the output of the static model, and this is really the steady state, is equal to the set point, right? And you can achieve this by taking a manipulated value, an input MV, that is the set point divided by the static gain. Of course, your information of the process is based on a model, so it will be the static gain of the model, right? So you can see that there is a hidden assumption, is that this model gain is exact, that you make the assumption that KP, the actual gain, is, well, the gain of the model. Well, there are of course some shortcomings with this first naive idea. Well, the dynamics of PV will be that of the open loop process, right? And you cannot influence this dynamics because there is no feedback. Well, you can also see that if your model gain is not exact, well, the actual steady state PV will be different to the set point, right? And you'll have a non-zero static error, right? And there is another thing that is not taken into account. Well, it's that on the actual process you have disturbances acting, and with this very simple idea we do not take them into account. Well, this is the implementation of our naive idea in the form of a block diagram. We have MV, which is set point divided by the gain in the model. So if we write PV, we see that we have KP, K over KP hat within, and the input is set point plus the disturbance dynamics, right, dV. And indeed we see that if KP is equal to KP hat, if dV is equal to 0, then we see that the steady state PV is equal to the set point, right? And we are going to go to set point with the open loop dynamics. Of course, we have seen that there are some shortcomings. In reality, KP is different from the gain in the model, and we have disturbances at the output, right? So in general we'll not have that PV will go to set point, and we'll have to do something about it. But you can kind of already see what we have to do from what we have done, for instance, for the Smith predictor and for the predictive PID. Well, to detect a mismatch between PV, right, and set point, well, what we can do is put a model in parallel. So we'll detect that we have a problem with the static gain and will also detect the presence of disturbances. So using this brilliant idea, we can put a dynamical model in parallel with the process and obtain the model error, right? And we'll use now, of course, a dynamical model, right? So this is the model error, and we can adapt our static model that we use for optimization. Well, previously we had just used the first part without the epsilon, but we know now that we make a model error, right? So if we want to impose that the steady state PV is going to be on set point, right? Well, we have to choose MV as follows. So it will be SP minus the model error divided by the gain in the model. And if we combine the two, we have now a first version of the internal model controller that will work better as the one obtained in step 1, in the sense that will detect problems with the static gain, will detect disturbances, but there will still be a shortcoming in the sense that the response to a change in set point will be still with the open loop dynamics of the process. Well, this is the implementation of the internal model controller that we obtain after step 2. Here in magenta we recognize the static optimization. We have MV is 1 over the gain of the model times SP minus the model error, and here you see the construction of the model error. We put a dynamical model in parallel to the system and we compare the output of the actual process with the output of the model to construct the model error, and this results in the following implementation. Well, using this second implementation of the internal model controller, it is not that obvious to see what will happen in steady state, right? And of course in the steady state we would like to have the steady state PV, I will write it like this, to go to set point. So to see this, we'll look at this control loop here in steady state, right? And in steady state, well, this model here can be replaced by a static gain Kp, and here in the model we can replace things by a static gain Kp hat, right? And we have seen that in steady state the MV steady state is 1 over Kp hat times set point minus the error that you have in steady state, right? So if we look in steady state, what will be the PV, and this is the output of the actual process, it will be, well, Kp times MV in steady state plus, well, some constant disturbance, right? So we'll have here Kp over Kp hat set point minus the error in steady state plus a constant disturbance, right? For the output of the model in steady state, we'll have, well, Kp hat, I'll write it down, Kp hat times the NV in steady state. So here this will simply be set point minus the model error in steady state, right? But the error in steady state, well, it's this one, PV in steady state minus the output of the model in steady state. So we'll have Kp over Kp hat set point minus kp over kp hat model error in steady state plus d, right, minus the set point minus the error in steady state. No, it's minus minus, so it's a plus over here, right? So this one we can take out, and what we can do now is isolate this one over here. So I'll write it down over here, kp over kp hat model error in steady state is, well, kp hat set point plus the constant disturbance minus the set point, right? And now we can write this one. I'll do it over here. So PV in steady state, well, it's kp over kp hat set point minus kp over kp hat model error in steady state, but that's this one, right? So we can subtract this one over here. So minus kp over kp hat set point minus the disturbance plus the set point, and then we have to add the disturbance, right? So you can see here that this one and this one will cancel out, this one and this one will cancel out, and we see indeed that the PV in steady state is equal to the set point. Well, let us have a look at, well, the step responses associated to IMC controllers from step 2. In the first case, we have here model is equal to process, and here we have that model is different from process. So here in this particular case, well, the time constant of the process and the delay are exact, but we have that the gain in the model is smaller than the actual process. The actual process is a Broida model, so a gain, a time constant, and a delay. If the model is exact, okay, so what we'll do is, since we have here a set point change of 10, well, the idea is that you use static optimization. We have a set point change of 10, so we induce a change of MV, that is the set point change divided by the gain of the system. So we have a delta MV of 5, right? And since there is no model error, this delta MV will, and no perturbation, this delta MV will ensure that PV will go to set point. Well, in this second case, the model that is used is correct except for the gain, as you can see. And as we think that the gain is smaller, well, this static optimization is going to lead to 10 divided by 1.5, right? So the MV kick here will be higher. During the period of the delay, nothing happens, but then, well, since you look at the model error, you will see that the actual process is evolving, well, faster than the model. So you will start to see a model error, and this model error is used to reduce MV. But in any case, as we had anticipated, even with a model that is not the actual process, we can still ensure that PV is going to go to set point. And what you can see also here in this step 2 implementation of the IMC controller is that we can kind of use this gain of the model as a way to boost the response. Okay, because you can see here, using the fact that the model gain is smaller than the actual gain, we have had here a kick of MV that is higher than if the model is exact. Well, in the following slides that I will leave for your information, we have cases where the step 2 IMC controller is used with the model correct except one parameter. In this case it is the time constant, and in this case it is the delay. And from these curves, what you can kind of learn that, well, indeed, even if the model is not exact, if the closed loop system is stable, well, PV will go to set point. From these types of curves, and by looking at the model error and by the comparison process and model, you can kind of learn also, well, what parameter is wrong. Well, as usual, there is a Simulink file available on the web page of the course that will implement this IMC of step 2, or IMC without boosting. We'll see why next. So the process is exactly the same process as in the slides. So it's a Broida model with these parameters, and here you have the IMC controller of step 2, and the tuning parameters are, of course, well, the description of your process. Of course, you do not know the actual process, so it is the description of the model of the process. But in this case here, we do as if the model is exact, and we can have a look underneath the mask, and you recognize this step 2 implementation. This is the output of the controller, well, sent to the process, and what we collect is PV. So here in between you have to imagine the actual process. Here you recognize the static optimization, so MV is obtained as set point minus model error divided by the gain of the model, right? And the model error is constructed by comparing PV with the output of the model. So you have seen the response with the model that is exact. Let's, for instance, do a simulation where the model is not exact and that we have an error, for instance, in the delay. So you can see clearly that there is an error in the delay because, well, the model in red has a dead time that is smaller than the actual dead time of the process. So looking at those types of responses, you can easily see that there is a problem and correct for that. But you can see that even if there is a mistake in the dead time, well, PV goes to set point. You can use this Simulink file to understand, well, the principle of step 2 IMC control. Well, this implementation of the step 2 IMC controller is probably the simplest IMC controller you can think of. And, well, the problem is that the closed loop dynamics are equal to the open loop dynamics, right? So it is the most simple IMC controller, but is nevertheless a very successful approach. What you could do to boost the response in closed loop is do as if the gain of the model is smaller than in reality, right? And what we have seen is this, well, boosting of the MV, and this clearly causes a faster closed loop response. But this is not something that you would like to do, right? You have to do as if the model is slow to boost MV, right? So what we'll do is use a step 3 IMC controller. In this step 3 IMC controller, you'll be able to boost the response, to accelerate the response, and you'll be able to use the correct model gain. Well, to illustrate this idea that you could boost the closed loop response by decreasing the model gain, let us look at the response when the model is exact, and this is what you obtain, right? And if I now will do as if the model as a gain of 1. Using this static optimization, right, we'll divide only by 1 instead of 2, so we'll have this MV kick that will be twice as high. This is what you see over here, and of course we have accelerated the response, right? So this can be done in this step 2 IMC controller to improve the time constants of the system in closed loop, so decrease the time constants in closed loop. But clearly we would like to have a mechanism that allows you to put the actual gain in the faceplate and have another mechanism to boost the closed loop response, and this is what we'll do in the step 3 IMC controller. Well, for this step 2 IMC controller, MV was constructed from the set point, right? And then we were subtracting the model error, and then we were dividing by the gain of the model, right? And this is leading to an MV, right? And in case of a set point change here, and assuming that we have a process with delay, well, MV will look something like this. So we have this kick, right, coming from the static optimization, and then we have MV that is constant for the period of the delay in the system, and then of course, well, the system is going to react. What we had done in the step 2, well, IMC controller is misuse this model gain, right? We have taken it smaller than in reality, and we could achieve a higher kick over here. But there is another way to have a higher kick, and the idea is that we want to achieve something like this. All right, and again, then when the process is starting to react, you'll deviate from this, and by looking at this now, you should kind of know what you should do, especially that it is written over here. You should use a lead lag filter in the control loop, so you should add a lead lag filter just behind this gain 1 over kp hat, right? Lead lag, and this lead lag has a, well, time constant t lead, and at the numerator, and a time constant, a lag time constant t lag. And to obtain that kind of response, you should use the lead larger than t lag. If this is coming as a surprise, this means that you have to go back to the section on process behavior. So this is the step 3 IMC controller with this boosting filter, this lead lag filter, and you can see this now as a form of dynamic optimization. Without the lead lag filter, we had static optimization, but now we want to accelerate things, right? And we'll see just after this slide how to choose, right, the time constants, the lead and lag time constants that you have in the lead lag filter. And as before, we have here, well, the construction of the model error. Let us have a look at the tuning of this lead lag filter, so the choice of the lead and lag time constants. We'll do this for a stable process that is a Broida process, so a first order with delay as given over here, and we'll assume that the model is exact, right? So kp hat is equal to kp and so forth. And of course, if the model is exact, the model error will be 0. Well, if the model is exact, epsilon is 0, right? We have 0 over here, and we can write PV as a certain transfer function, and at the input, the set point, we'll assume here that the tv is 0. So we obtain, if the model is exact, pv, well, the model is exact, so this one and this one will cancel out, right? So we'll have p din. This is the open loop dynamics without the static gain, right? And we'll have the lead lag filter. So the lead s plus 1 over t lag s plus 1 set point, right? So in this case, where the model is exact, well, the relation between set point and PV is the following one. Well, and indeed, if the model is exact, we obtain the ideal closed loop response, that is this one. And in our particular case here, where we have considered a first order system with delay, this is what we have called PDIN in the previous explanation. So it's the open loop dynamics without the gain. By the way, the IDs here for a first order with delay can also be extended to higher order systems. So this is the ideal closed loop response that we want to boost, right? So what we can do is choose the lead time constant of the lead lag filter to be equal to the time constant of the process, so that this part here and this part here cancels out, right? We can do this because, well, what is cancelled here is a pole that is stable. So we obtain in this particular case an ideal closed loop response, that is this one. And of course we would like to accelerate the system with respect to what was obtained in open loop. So we'll take this lag time constant of the lead lag smaller than the open loop time constant of the process. As usual, we'll write this lag time constant of the filter and the lead lag filter as a parameter gamma times the open loop time constant of the process. And we can accelerate things, but of course we have to do this within certain limits. So we'll take gamma in between values 0.2 and 0.9, and of course these are indicative values, right? Of course, the smaller gamma, the faster the closed loop response, but also the more aggressive the control. So you can see here that the closed loop response is shaped using this lead lag boosting filter. So we could call this filter also a shaping filter. Well, let us take the example of the step 2 IMC controller. We take the same process. So here is what we had obtained with the step 2 IMC controller in the case where the model is exact, right? This is actually the case in, well, the two simulations here. The model is exact, but this is the step 2 IMC controller, so there is no boosting, as you can see. This means that, well, the dynamics in open and closed loop are the same, right? But here what we do is use a lead time constant that will compensate the time constant of the process, right? And we take a lag time constant in the filter that is smaller than the time constant in the model or the process, because here the model is exact. And this will of course boost the response, and this is clearly seen on MV here, but you can see here that, well, both the output of the model and the process, since the model is exact, is accelerated. If you look at the time constant in closed loop here, in this response it is smaller than in this response. Here we have a closed loop time constant of 5 seconds, and here the closed loop time constant is 3 seconds. So we have accelerated the response in closed loop. In summary, in this step 2 IMC controller, the open loop dynamics is equal to the closed loop dynamics, except if you misuse this model gain KP hat, but this is clearly not desired. And in this step 3 controller, IMC controller, you can boost the closed loop response to a desired closed loop time constant by choosing the lead lag boosting filter appropriately. Clearly, the steady state analysis that we had made before is still valid, because we only have introduced in the closed loop a lead lag filter that has a static gain 1. So even if the model is not exact in this IMC controller of step 3, well, PV is still going to go to set point. Well, indeed, this is what you see here on the right. The model is exact, except that KP hat is smaller than the actual gain, but you can still see that PV is going to go to set point. If you see that kind of curve, well, you can clearly identify that the gain is wrong from the fact that there is a steady state error. Here you see a problem in the model with respect to the time constant, right? But again, still PV is going to go to set point, and here you have a problem in the model with the delay, but again you can see that PV is going to set point. On the web page dedicated to the course, you will find a Simulink file that also allows you to implement the IMC controller of step 3, so IMC with boosting. The process is the same. If you look at the faceplate, well, you have the model parameters. Now you have also the lead and lag time constant of the boosting filter, and if you look under the mask, you will see, well, the same type of IMC controller, except that we have added here the lead lag filter. So again, you can use this Simulink file to understand the principle that is behind, well, this step 3 IMC controller. Well, let us have a look at the final version of the internal model controller, and this is the version that you'll find in the literature, in the books. So what we'll do is again use a model of the process. So this is the actual process. It is described by P, and here we have the model. Here P now is a transfer function. So we take the dynamics into account, and this is our model. Since our model is inexact and since we have disturbances, we add epsilon, and this model error is constructed as before. The idea of optimization is the same as well, but now we do dynamic optimization. Previously we were only using the static model. So if we want the output to be equal to the set point, you can see here that, well, MV should be chosen as SP minus epsilon, and then you have to invert the model, and this is how you can construct your manipulated value, right? But as you can imagine, this one is not always realizable in practice, because the model might have a delay and you cannot, well, take the inverse of the delay, and, well, this will lead to pole zero cancellations, and these are allowed only if they lead to stable pole zero cancellations, so of poles and zeros that are to the left of the imaginary axis. So in reality, we'll not be able to work with the inverse of the model. We'll have to approximate it, and we'll call it P inverse. So this is the, well, P that you have when you invert it, taking into account all the constraints. What we do is also add a filter F for robustness. Sometimes it is necessary to add an additional filter to filter the model error, and we will see that this filter can also be used to improve the rejection of output disturbances. Well, this is the final version of this internal model controller in block diagram. You can see that the model error is constructed as before, and MV is constructed right from an approximate inverse of the process, and we add this lag filter for robustness. So this is really this dynamic optimization, and this is the construction of the model error. And we had said that, well, in some cases, well, it's necessary to filter epsilon because there is noise on PV and therefore also noise on epsilon. Well, let us make the link with the step 3 internal model controller, and we'll do this for a process that is a Broida model. So we'll have here Kp over Ts plus 1 and the exponential of minus theta s, and of course we'll construct the IMC controller using a model, right? So let us do this, and what we'll do is first look at the approximate inverse. Well, the delay we cannot invert, right? So we'll have to take the inverse of this one, and since we're using a model, we're going to have 1 over Kp hat T hat s plus 1, right? And this is this part over here. Well, this we cannot implement because the relation is not proper, but if we add a lag filter, and we'll draw it over here, well, we can give it a time constant t closed loop s plus 1, right? We have here the overall transfer function that takes into account the lag filter and the approximate inverse, and you can see that we have something similar than what we had obtained for the step 3 controller. So here 1 over Kp hat and then a lead lag, right? That will compensate the pole of the system, and we take here a closed loop time constant that is smaller than the open loop time constant. So this version is more general. Well, note that this final version of the internal model controller, and all the other versions, by the way, is constructed for set point tracking. But what you can do is, well, obtain a version that is an improved version that will also improve the disturbance rejection. And the idea is as follows. Well, you can see that, well, the disturbance variable goes through the dynamics, and this signal over here, well, let's call it dV bar, right, is influencing PV. So you have one path of influence on PV, but here this PV, right, is also going to influence epsilon, and you have created, using this feedback, a second path of influence, that is this one over here, right? And what you would like to do is to make sure that this second path of influence compensates the other, right? So here we have plus, minus. So okay, from a sign point of view, everything is correct. So we would like to have that in this chain here, the transfer function is approximately 1, right? So what you can say is that, well, this approximate inverse, right, will approximately compensate the process dynamics. So here we can, in approximation, cancel out this one, right? So we still have this filter F, right? So to have a loop gain here in this part in blue of 1, what we should do is invert the filter that you have over here. But this filter is a lag filter, so of course this is not possible because we would have something that is not proper. So what you do is multiply by another lag filter, but with a smaller time constant so that this is now realizable. And in that way you have created a path of transfer function that is approximately 1, not exactly, and this will improve the disturbance rejection. Well, this filter for improved disturbance rejection is not going to affect too much the dynamics of the setpoint tracking as long as this error here epsilon is small enough. And in steady state, if you make sure that the static gain of this filter is 1, then we can keep the IDs of our static analysis that we have made and ensure that indeed PV is going to go to setpoint, and that will have a 0 steady state error. Well, here we have the final IMC internal model controller, and here you can kind of see that this controller is a standard controller in the sense that it has an input setpoint, an input PV, and an output MV. Well, this internal model controller, we would like to rewrite it as a equivalent series controller. And a series controller is a controller that is acting on SP minus PV. So it's acting on the control error, right? And we would like to rewrite this internal model controller using this C equivalent, and here at the output of course we have MV. So let us try to do this. What we can see over here is that MV is indeed P inverse times F acting on SP minus epsilon. This is this dynamic optimization. Well, and epsilon we can replace it by PV, right? This is coming from the process, minus P hat MV. So this is MV going through the model. Well, this is the equation that we had obtained in the previous slide, and now you can rewrite this because you have an MV dependence over here and an MV dependence over here. We take everything that has a dependence on MV on one side, right? So 1 minus P-inf F P hat, right? So we have this side over here, and here we have P-inf F acting on SP minus PV. So this is the control error, right? So we can see here that MV is really this controller, this equivalent series controller acting on the control error, right? So we have been able to rewrite this internal model controller as a series controller, and an equivalent series controller. Here we have obtained the equivalent series controller using equations. You can also obtain it by reorganizing this block diagram. So let us start with that. As you can see, there is nothing that is changing over here, and here, well, we have the minus here and the minus here. So what we could do is take this one and take it over here. But since we have minus and minus, then we have a plus over here. And this is what is done over here, right? So this is now the equivalent series controller, and it is indeed acting on the control error SP minus PV. And if you compute this transfer function, right, it will be, this is then the equivalent series controller. Well, it will be this one that is in the forward part, F P inverse over 1 minus, because we have a plus here, and then what you have in the whole path. So it will be here F P inverse P hat, and this is indeed what we had obtained before. Well, it is of course also possible to combine an internal model controller with the feedforward. We'll have to assume here that the disturbance value dV is measured. So you can use the idea of feed forward, and remember here that we'll have a transfer function that will be this one, dynamics of the disturbance divided by the dynamics of the process. Remember that this is not always realizable and that you'll have to take precautions, right? Of course, since you implement the feed forward on DV, you would not like the internal model controller to react to the presence of disturbances over here. So what you'll have to do is in your model add the influence of the disturbance as well, right? Using a disturbance model. In such a fashion, if the model here of the disturbance is exact, well, here in epsilon we will not see this disturbance, which is good because it is compensated by the feed forward. Well, at the end of this course we have to make the link with the IMC tuning parameters, right? Remember these tables that we have used to tune a PID controller, and we'll see how you can obtain the IMC tuning parameters for one particular transfer function or process, which is the Broida process, so a first order system with delay. The equivalent series controller that implements an internal model control is this one, and in general it is a high order controller, right? And in one particular case, when the process has delay, well, you'll have a delay here in p hat at the denominator, and we cannot really write between quotes the transfer function in that case, and we'll say that the controller has an infinite order. Remember that this internal model controller will cancel part of the process, so you'll have to make sure that there are no unstable pole zero cancellations because they go against internal stability. Sometimes, as we have seen in this example with poor load disturbance rejection, sometimes it's not even a good idea to cancel slow poles of the process. So the idea is that you design an IMC controller, an internal model controller, that you obtain the equivalent series controller, and then that you make some approximation of the delay using a Padé approximation. So a Padé approximation is, for instance, exponential of minus theta s is approximately 1 minus theta s, and this is obtained from the Taylor series of the exponential. So in this equivalent series controller, if you do that type of approximation, well, often you come up with a PI controller or a PID controller, right? And then you obtain the IMC tuning parameters. In such cases, you have to not forget that in order to do the approximation, the Padé approximation here, we have to make the assumption theta small enough, and in most cases it's theta small enough with respect to the desired closed loop time constant. Well, let us find the IMC tuning parameters for the first order system with delay, so for this particular transfer function, and we'll assume here that we have an internal model controller where the model is exact. What we'll need in the internal model controller is, well, the approximated inverse, and here it is. The only part that we cannot invert is the delay, so here we have the approximate inverse, and here we have the robustness filter, so we simply take a first order filter, and we had seen that we could choose the time constant to be the desired closed loop constant. Right, notice that this one is not proper, but anyway, what is happening is that these two are used in series, and if you multiply those two, you have a proper transfer function. So what you can now do is compute the equivalent series controller, and if you go through the calculation, this is what we obtain. And this is what I mean, you cannot write this because you have a delay here at the denominator. So strictly speaking, we should not write something like this. And what you could do is use approximation, Padé approximations of increasing order. So the simplest one is this one, but there is a Padé approximation of order 1, that is this one. We have seen this. And you could go to Padé approximations that are of higher order even. And if you inject those rational approximations of the delay of increasing order, you can kind of see that this equivalent series controller is a controller of infinite order. What we'll use in this case here is this approximation over here, right? And if we inject this approximation in here, we end up with this approximated equivalent series controller, and you can rewrite it differently, and now you recognize here the form of a PI controller, where this is the controller gain, right, and this is here the integral time constant, right? And if you go and look at the IMC tuning table for first order with delay, you will see that the controller gain can be written as follows, and the integral time constant is, well, the open loop time constant, and this certainly makes sense. If you use this approximation, but this will be much more difficult in the calculations, you'll obtain the PID controller, and you'll obtain the IMC tuning parameters for a PID controller. The next section, section 8, applies IMC tuning to all kinds of control structures related to, well, the DC motor and its position and speed control. I will leave it for your information. There is also a section 9 with, well, a dictionary and translations for different controller terminologies in 4 languages, and I will leave it for your information as well. This concludes this video course, Practical Process Control. I hope you liked it. Do not hesitate to react if you liked it or not, if you see mistakes or typos, or if you have ideas for improvements. Thank you very much.